In this screencast, I'm going to focus on the derivation of the trajectory equation. So we're going to start with the two-body equation of motion. So here is the situation. So we have a gravitating body, could be a planet or it could be a star, but it is the sole source of gravity in the problem. And this blue point here is the position of a spacecraft, and the red vector going from the center of the gravitating body to the center of the spacecraft is the radius vector r. And the two-body equation of motion tells us the force, or equivalently what the acceleration felt by the spacecraft will be in the presence of that gravitational field when it's at a position r and it's in the proximity of an object whose gravitational parameter is mu. And remember that the gravitational parameter is just the product of the gravitational constant and the mass of the gravitating body. So the first thing we'll do is just take this right-hand term and bring it over to the left just to make things a little tidier. And then what we're going to do is take the cross product of the equation of motion with h, which is the specific angular momentum. So h is also a vector. Let's look at this first term. So we've got these two dots. So this is the second derivative of the vector r multiplied by the specific angular momentum h. And I can simplify this by recognizing that the second derivative of vector r crossed with h is equal to the differential, the derivative with respect to time of the first differential of r crossed with h. And to see that, you simply expand out that differential. So you apply the product rule, and we have that d by dt of this first differential of r crossed with h is equal to the differential of that first term crossed with the second term. In other words, the second derivative of vector r with respect to time crossed with h, plus the first term crossed with the differential of the second term. In other words, plus r dot, the first differential of r with respect to time, crossed with the first differential of specific angular momentum with respect to time. And you know that the specific angular momentum of a spacecraft in the two-body problem is a constant. So the differential of specific angular momentum must be zero. And that means that that final term disappears. So we've now replaced the expression that I've just derived into the equation of motion crossed with h. So that's the first term dealt with. Now let's look at the second term. So the second term is simplified by recognizing that h is actually just vector r crossed with vector v, the velocity of the spacecraft. And so I can rewrite this with a scalar, with a vector triple product. And now what I can do is use the back cab rule. That's the vector identity which relates the scalar back cab terms to the vector triple product. And so in this case, r is going to take the place of a, the second r takes the place of b, and the velocity v takes the place of c. So when I use that identity, I find that my equation of motion second term can be rewritten as this combination of scalars. And this second set of the second scalar is the easiest one to deal with, because I know that a vector taken as a scalar product with itself is just a scalar, and it's the square of the magnitude of the vector. In other words, vector v multiplied by the scalar product of r with itself is just equal to vector v multiplied by r squared. So that's the term that we're working on. This is where we've got to so far. What about this part of that expression? Well, v is just r dot. So it's the first differential of vector r with respect to time, it's the velocity. And that turns out to be quite a useful, if trivial, change to make, because we can identify another vector identity which allows us to simplify further. So to see that identity, let's derive it. So let's look at the vector r in a scalar product with itself, and we know that that's going to be r squared. If I want to differentiate this scalar product with respect to time, so d by dt of vector r in a scalar product with itself, I use that identity, so I can see straight away that that's the same as d by dt of r squared, the scalar, which is equal to 2r dr by dt, and I can write that as 2r multiplied by the scalar r with a dot over the top. But I can also do that differential using the product rule. So the product rule tells us that d by dt of this scalar product is equal to r multiplied by, or in a scalar product with, dr by dt plus dr by dt, so that's the differential of the first term, multiplied by the second term. So dr by dt, in this case, in the scalar product with r. These two terms are the same, so I can rewrite this as 2 times r in a scalar product with dr by dt, and that's equal to 2r dotted with the first differential of the vector r. So the result is that this scalar 2r times dr by dt is equal to 2 times the scalar product vector r dotted with the first differential of vector r. So I can write that down, and I can see that I can use this identity to simplify this term, because my 2 cancels out on each side, and I get vector r dotted with the first differential of vector r is equal to the scalar r times the first differential of the scalar r. So if you remember that, my expression now becomes a little more simple. You can see now that when I expand this out, I'm going to get 2 terms. The first one is a term which includes an r, that's a scalar r, and 1 over r cubed, so I'm going to get a term in 1 over r squared here, and the second term includes an r squared and a 1 over r cubed, so I'm going to get a term in 1 over r. So I just expand that out, and that is indeed what I get. And we find that that can be rewritten as minus mu d by dt of vector r over r. And what you should do is just write this out and satisfy yourself that that is the case. So we apply once again the product rule, so minus mu d by dt of vector r over r. I can evaluate that differential as the differential of vector r multiplied by 1 over r plus vector r multiplied by the differential of 1 over r. So perform that differential, and we end up with 2 terms, and those 2 terms can be simplified to provide us with the expression that we began with. So we find that this second term in my two-body equation of motion crossed with h can be rewritten as minus mu d by dt of vector r divided by the scalar r. So we started with the two-body equation of motion. We crossed it with the specific angular momentum, and we end up with this new expression for the two-body equation of motion crossed with h. Both of the terms are differentials with respect to time. If I integrate those terms with respect to time, I know that I'm going to get a value which is a constant because the differentials are 0. So I'll do that integration and I end up with a term in r, vector r dot crossed with h, and a term in mu vector r over r. So if I name the constant of integration b, and I do a little bit of rearranging to get my mu term back on the right hand side, which is where we began with, I end up with this vector cross product being equal to mu times vector r over r plus this vector b. So just to be clear, b is the constant of integration that we get from doing this integration, but a constant of integration can be a vector, because a vector is just 3 scalars multiplied by 3 unit vectors. So that's perfectly reasonable result. So that's what we've got now. If I take the dot product of that expression with r, I'll get a scalar relationship. So I take the scalar product of this expression with r, and I end up with these two simple terms. Once again, I can use a vector identity. I can use the scalar triple product on the first, on the left-hand term. So I end up with r vector crossed with the vector dr by dt dotted with h on the left-hand side. And I'm not going to do anything with the expression on the right-hand side because it will lead to a simplification without any further steps. So let's just look at this term. So r crossed with r dot is equal to r crossed with v, and that's h. That's the specific angular momentum. So this expression, this side of the equation, becomes h dotted with h, which in other words is just the scalar h squared. And all I do is expand out the right hand side and I get these two terms in mu and r and b. And because this r dotted with b can be written as the magnitude of r multiplied by the magnitude of b times the cosine of the angle between them, I write that as rb cos theta, where I'm just labeling the angle between those two vectors as theta. So rearranging, I get h squared equals mu r plus rb cos theta. I can make r the subject of this, so divide through by mu, gather the terms, and I end up with an expression which is starting to look very much like the trajectory equation. So I have the radial distance of the object from the gravitating body r in terms of the specific angular momentum, the gravitational parameter, and 1 over 1 plus this b over mu term multiplied by cos theta. So that's what we've got. And if you remember the derivation of the polar form of the conic section. That ends up as being r is equal to p, where p is the semi-parameter, which is the vector from f, or rather the scalar, from the focus in a direction parallel with the minor axis, in other words, at a true anomaly of 90 degrees. So p divided by 1 plus e cos nu. And if we compare these two expressions, the one that I've just derived and the simple expression, the polar expression for a conic section, I find that these are directly comparable. And by comparing them, I have some identities which I can now use in further work. So I can see, for example, that h squared over mu takes place of p. So I can write that p is equal to h squared over mu. I can see that b over mu here is in place of e. So e is equal to b over mu. And I see that the angle between r and b, which I gave the label theta in the derivation, is in fact found to be the true anomaly nu. So theta is equal to nu. So finally, I've set up a little spreadsheet which allows you to see the effect of these parameters. So this is the trajectory equation coded into Excel. Just a few little extras. So this blue ellipse is the full orbit plotted on the graph. The green circle represents, in this case, the radius of an object, the radius of a gravitating body. The red square represents the position of the satellite. The black line is the radius vector between the center of the gravitating body and the center of the satellite. And I can control all of these parameters plus the eccentricity, the semi-major axis, and the semi-parameter of the orbit down here. So at the minute I'm showing the spacecraft at a true anomaly of 353 degrees. So let's set that to 0, and I find that the object, the spacecraft, is at the point of closest approach. And of course that's the definition of the periapsis, and it's the periapsis vector from which the true anomaly is measured. At the minute, this is an orbit with an eccentricity of 0.3. If I give that orbit an eccentricity of 0, then I have something which is effectively a circle, or in fact is exactly a circle, but the resolution of the spreadsheet that I've set up means that it's rather polygonal. Let's make this a little bit more obviously eccentric, so let's give it an eccentricity of 0.5. So now we can see that the gravitating body is at one focus, the other focus is empty. The semi-parameter p corresponds to a true anomaly of 90 degrees. So if I set this to 90 degrees, I can see that the spacecraft is the radius vector of the spacecraft is parallel with the semi-minor axis. So this is actually a very simple spreadsheet. So you can see the formula bar up here. So the true anomaly is just a value. The semi-major axis is just a value. The eccentricity is just a value. And the semi-parameter, well, I calculate the semi-parameter by taking the semi-major axis multiplied by 1 minus the eccentricity squared, and that's an expression which is derived early on in the astrodynamics course. So r is not just a parameter. In fact, r is the trajectory equation, and it's the trajectory equation in this case using p, the semi-parameter, rather than h squared over mu. But when you know one, you can go to the other. So I can change my semi-major axis. So let's reduce the value a little bit. So these are in units of meters. So I'm going to change the orbit to a smaller orbit, and I can see that as I increase nu, the true anomaly, the spacecraft advances in its orbit around the gravitating body. So the apoapsis is at a true anomaly of 180 degrees. So that's the point of most distant approach. And the periapsis is at a true anomaly of 0 degrees. So the spacecraft moves back to the point of closest approach.